Okay, welcome again. This is our third week, I believe, and I think this is the last week of instruction before the midterm test, because I would like to clarify this. I've got a few emails because I sent an email yesterday and somebody was asking me what this means, the last week. No. We operate by weeks. Like each modules represent the week. That means this is the third week, which means last week before the midterm means the next week will be the midterm week. Okay? And midterm is due the same like each weekly quiz, which this means Monday, but the next week, the fourth week, will be we will have a review, of course, the midterm exam review, and the midterm will be open Thursday or Wednesday. I have the calendar. June 7th. June 7th, I think, is Thursday or Friday. Oh, I don't. Okay, June 7th, the midterm will be open and will stay open until Monday. That means you may choose any date in this time frame on any date on Examity. Okay? Any day, any time on Examity, and you will take the test through the Examity, because this is the midterm one. This is the first test that is proctored. Each midterms and final are proctored. Okay, I mean, I hope this makes sense. I mean, I was a little bit surprised that the confused, but I mean, I just got maybe one or two emails, but still, I would like to clarify. That means this is the last week of instruction. Okay, and I hope everybody, I saw almost everybody had a time slot on Examity. If you don't have it, I still recommend to do really fast. Like, I think I said this at my first session, okay, of the test, of the course. That means you really have to, because the last minute booking is not a good idea. The times could be taken and then you will not be able to take before Monday midnight. Okay, that's what we still have. We still have chapter 2, and in chapter 2, we have 4 sections. That means I will try to cover today section 2.5, the chain rule, section 2.6, which is implicit differentiation, and then I will probably, we will see, depends on the time, but I will provide for you the video for section 2.6 and 2.7 and 2.8, which 2.7 is the application of derivatives, quite quick and easy section, but 2.8 is the related rates. That means I can show you the steps, I can show you the guidelines, how can we solve these problems, and I can solve a few problems. That means depends. Maybe I can do today. If not, I will provide a video for you, okay, to watch. Okay, but let's start with 2.5, the chain rule. Do you have some questions from the previous week? If not, it's okay. I mean, you can always use the chat box, you can always use the discussion board later, or you can email me. Okay, that means chain rule. What we have, I will switch off my video because it's covering my screen. How can I switch my video? Okay, then it's better. Okay, that means chain rule, it's like another rule of differentiation. We learn how to differentiate a power function, a product rule, the quotient rule. That means now we will talk about the chain rule. Okay, that means chain rule will be important, and we will apply that rule if we have to differentiate a compound function, right? Like a composition of 2 functions. If we will look at the formula and we will see kind of like 2 different functions. Okay, like for example, I will explain this slide, but if I will ask you to get the derivative of square root of sine of x, for example. Okay, that we can see, we kind of see the square root, but also inside we see another function. Okay, that means we call this compound function or composition of 2 functions, and we always have a outer function and inner function. And this is the notation from algebra class. F compound with G. F means the outer function, G means the inner function, and that's how we can rewrite. F compound with G. That means having a formula for F, and instead of F, I mean instead of X in the formula of F, we will substitute the new function, G of X. Okay? And the domain is always we have to take under the account both of the functions. Okay, that means now what I will do, I will show you two functions, F and G, and hopefully we will try to get correct composition. That means let's compound F compound with G. Do you think you can tell me the answer? What will be the solution? What will be the final function if I will compound? Function F is x squared. G of X is sine of X. Okay, that's what we have to do. We have to take function F and instead of X, in function F, substitute G of X. Okay, that's we can see. I didn't type in taking function F and substituting G of X. And function F was x squared. Okay, I can write x squared, but I don't want X, I want G of X. And that's the answer. G of X was sine of X squared. And one more notation, because for the trigonometric function, we know that this is equivalent notation. Sine of X squared means sine square of X. And as we can see, even looking at this function, we see two of them. We see power function and we see trigonometric. Okay, maybe the next one you will answer. Square root of X, that's f of X, and G of X is 5x cubed. That means, do you think you can tell me the composition? F, function F, which is square root, compound with G. Oh, you can type the answer. You can try to type the answer if, oh, thank you. Thank you. I don't know the name exactly. You can change your name on the Zoom, but if it's okay, that means we have to just simply take square root as a function, outer function, and inside will be 5x cubed G of X. Okay, and then I have another one, tangent of X and 1 over X. And what will be the composition? F compound with G. Function F is tangent of X. But now I want tangent of G of X. Okay, this means F compound with G, which means tangent of G of X, okay, which is tangent of 1 over X. I can also do the other way composition, just to double check. This means that I want to function G be the outer function. Okay, that means G compound with F. Function G is defined as a 1 over X. But I will put a new function, f of X, tangent X. Okay, as we can see, it's different way composition, but still we see two functions, 1 over and tangent of X, tangent of 1 over X. Okay, that means now it's really important, extremely important, to identify the inner function and the outer function. Okay, because we're looking for the derivative of the composition of two functions, and basically it's really easy, because derivative of the composition function f compound with g is simply a product of the derivatives of f and g. Okay, I can actually write down. If function f of x is defined as a composition f with g, which is f compound with g, I can write a little bit closer, then derivative of this will be derivative of f times derivative of g. Right? It's just the product f and g, outer function and inner function. but function, which is the outer function, will still depend on the inner function, and the inner function depends on x. Okay, that's me. This is the only tricky part. Okay, but the general definition, the general formula is f derivative of f times derivative of g. But still remember, f depends on g, and g depends on x, is the inner function. Okay, that means let's try. And I do have this notation that I just wrote for you, and we also have a Leibniz notation. Dy dx is the other notation for the derivative. That means we will differentiate function y with respect to u and function u with respect to x. If I will say, because we don't, oh yeah, we see you. Okay, we do see you. Okay, because I may have a function f in terms of u, which will be f of u, derivative f of u is f prime of u, but we still have to remember u is an inner function. That means this is, and we call this chain rule. Okay, chain rule, and this is the same. We still have to differentiate chain rule. That means u prime means du dx. Okay, but derivative of the outer function f is f prime, but depends on u, and this is that u. Okay, that's me. Let's see based on exact function. One more slide to explain everything, because I know that later you're watching the video again, or the students that not attending a session, the live session, they watch, and you can pause the video and you can digest every single formula. Okay, now it's my example. Okay, find f prime of x if f of x is defined as a square root of x squared plus 1. Okay, that we do see the outer function square root because it's outside, and inner function is x squared plus 1. And what I will do, I will name the inner function u. Okay? That means the inside quantity is u, x squared plus 1. Then my function in terms of u looks like square root of u. Nice and easy. Okay, square root of u. And now I have to differentiate function f. Derivative of square root of u, we remember from the previous class, and we may use the power rule, but I recommended to just know derivative of square root of u is 1/2 square root of u, and times derivative of the inner function. That's my chain. Okay? That means derivative of square root of u, it's 1/2 square root of u times derivative of u. But I still want to end up with my x variable. That means instead of u, I will put back x squared plus 1. X squared plus 1, x squared plus 1. However, this one I have to differentiate. Derivative of x squared plus 1 is 2x. Okay? That we can nicely see, and this stays. Okay? That means that's what the formula was telling me. Derivative of the outer function times derivative of the inner function. Outer function is square root. Derivative of the square root is 1/2 square roots, and the same square roots, x squared plus 1, x squared plus 1 inside, times derivative of x squared plus 1, which of course is 2x. We can simplify a little bit. We can simplify that too and put x on the top. Okay, that's the derivative of the compound function. Let's do another one. Okay, find f prime of x if f of x is sine of x squared, but please note that this is together. The sine is not squared, just the x squared. That means the outer function is sine in this case, and the inner function is x squared. That means the inner function u is x squared. Okay, that means I have just sine of u. Now, of sine of u, Actually, can you tell me what is derivative of sine of u? Sine of x, that's the same thing. What's the derivative of sine function? Cosine of u, thank you. That's mean derivative, yes, thank you. Demetrius and Jillian. Okay, derivative of sine of u is cosine of u. We can see cosine of u, but follow the chain rule times derivative of the inner quantity, derivative of u. That's my chain. Okay, and let's substitute instead of u, x squared. Okay, that means this will stay cosine of x squared times derivative of x squared. Derivative of x squared is 2x, and the only thing that I can do, I can place this in front, because I can't combine quantities outside with an angle. Okay, 2x times cosine of x squared. Example number 3. Find f prime if f is sine square of x. That means now the situation is a little bit different, because sine square of x means sine of x squared. Okay, the whole function sine of x is squared. Okay, that means my inner function in this case is sine of x. That's my inner function, u, I can name u. And I'm squaring u, that means power function is an outer function. Okay, u squared. What's the derivative of u squared? Probably everybody can type really fast. Yes, thank you, 2u. That means 2u times, please remember, times derivative of u. That's the chain. I can remove this. That means u squared is 2u. But now we have to remember that u also has the formula behind. And let's substitute back. U was sine of x, and derivative of sine of x, it's cosine of x. Do you recognize this formula? Maybe not. Maybe it's the double angle formula, but we don't really have to know at the moment. I think calculus 2 is more important. But just yes, this is equivalent formulas. But 2 sine of x, cosine of x is still the good answer, because we're learning a chain rule. Okay, let's see my next one. Oh, okay, I don't have the next one. That means I do have these. And this is just here, just one more time I type example number 2 and example number 3. Kind of like more explanation. Just to know the difference between sine of x squared and sine of x squared. Okay, but you can read this, you can pause the video and like go through again. Okay. What I have, I type for you the trigonometric formulas, which we know, the derivatives of the trigonometric function, but now I will apply a chain rule, which means every single angle probably is represented by another function. That means we will have not just sine of x, we will have sine of another function. Okay, that means sine, cosine, tangent, cotangent, secant, cosecant. That means derivative of sine, we know that is cosine of u times u prime, because we have to remember, we have to check, possibly u is another function. Okay, derivative of cosine of u is negative sine of u times u prime. Tangent of u, actually, can you tell me tangent? What's the derivative of tangent function? Secant square, thank you. That means secant square of u times u prime. Cotangent, who remembers derivative of cotangent? No? We really have to know them. It's just the 6 formulas and it's so easy to remember them. You probably noticed that all of the, yes, negative cosecant. Negative cosecant square u and u prime. Okay, secant of u, do you remember the derivative of secant? Secant tangent, that's me now. Okay, now let's see. Derivative of secant of u is secant u tangent u, and times u prime. because the only mistake sometimes, you kind of writing u prime and u prime, but that's not, no, because we see like two functions. But no, this is just a formula. Derivative of secant is secant tangent u, and times u prime, because that was the inner function. We don't have to repeat twice. And respectively the same for cosecant. Cosecant of u, derivative is negative cosecant u, cotangent u, times u prime. That means from now on, always remember about the chain rule, the inner function. Okay, and I do have power formula for you. That's mean now derivative of u to the power of n. Like let's say x to the power of 10. We know what's the derivative. Of course, it's 10 x to the power of 9. But and now we have to really check if this function, if this x is just x. If it's just x, it's fine. But if it's another like formula, we have to multiply by derivative of x, which actually derivative of x is 1. Also the chain rule works. That means now I will name this function u to the power of n. Derivative is n, u to the power of n minus 1, times u prime. Or I use du dx notation. Okay? And the same thing. Instead of u, I put g of x. G of x to the power of n. Okay? That means that's n, copy the same function, n minus 1, times derivative of that inner function, g. Okay? That means that's the chain. The same for this one, chain rule. Okay, let's practice a little bit of power function. Differentiate quantity x cubed minus 1 to the power of 10. That's we have to differentiate this. And I think I'm not using a u notation, but if you like, I can still write this u notation. Because normally we will not use as a learning tool, yes, but later probably you will get so confident and we will skip this. Okay, that means what's the derivative of u to the power of 10? I can write a little bit. U to the power of 10, everybody knows 10u to the power of 9, but still multiply by derivative of u. All right? That we can see I did this, but without really writing u. This is my u. Okay, that means u to the power of 10, u to the power of 10, derivative is 10, u to the power of 9, and this is u prime, times u prime. Yeah, we can see the same thing, or if you like, and I know that some students, they don't really like the u notation, they really like, they see the expression here. Okay, but I still know that some of you likes this. Okay, that means quantity to the power of 10, u to the power of 10, 10u to the power of 9 times u prime. 10u to the power of 9, and derivative of inner function is just 3x squared. And the only thing is I can combine 10 and 3x squared. That's my final answer. Okay, okay, that's the chain rule. Okay, let's see another one. Ooh. Differentiate 1 over cube root of the quantity x squared plus x plus 1. That's been what we can do. We can definitely rewrite this function as a quantity x squared plus x plus 1 to the power of negative 1/3. I actually have here. Okay. Or if we like, we can write u to the power of negative 1/3. That means derivative of u to the negative 1/3 is negative 1/3 u to the power of negative 4/3 times u prime. That's my chain. Okay. That means I'm not writing my u. Quantity to the power of negative 1/3, one more time. Derivative is negative 1/3 u. Okay, we can say this is u prime. Negative 1/3 quantity to the negative 4/3 times derivative of this quantity. Derivative of x squared plus x plus 1 is 2x plus 1. And also, we have to rewrite in terms of positive exponent. That means I will place everything in the denominator because quantity to the negative 4/3 means cube root and quantity to the power of 4 and everything placed in the denominator. Okay, that we can see this 3 is telling me that the root must be the cube root, 4 will stay as a power, and negative, it's telling me to put everything in the denominator. Okay, this is nice form. Okay. I will really suggest to do all of these questions, all of these problems one more time. You can look at the question, cover the solution, and try to do on your own. Okay? Because looking at the solution, it's nice and easy and looks trivial, but solving on our own, it's a different story. Okay, what else I have? Oh, that's nice function. Quantity to the power of 9. Okay, I don't even have to read u to the power of 9. Derivative is 9, u to the power of 8 times u prime. Let's see. 9 quantity to the power of 8 times derivative of this quantity. Okay. That means 9 u to the power of 8 times u prime. That means I will copy this part, and for the derivative, what I did use the quotient rule. And that means you can also practice the quotient rule. Derivative of the numerator is 1 times denominator minus x minus 2, which is numerator, times 2 derivative from the denominator squared. And then I can simplify the top here. And I also see 2x plus 1, because I can actually rewrite this to the power of 8 and this to the power of 8. The top and the bottom. My 8 is not clear. And 8 and 2 I can add together is 10, just to have a nice combined form. 9 times 5, 45. Okay? But what is important for me? Important for me is, of course, the chain rule. The rest of them is relatively old. Okay, another thing what we can do is when you learning a new rule, we can apply the rule, and we can apply even not once, we can apply a few times. That means you may see a function that actually has not only one inner function, we will have more inner functions, which we have to keep integrating and keep differentiating. I'm sorry, because I'm also integrating in my life. We will integrate. We have to keep differentiating until we reach the most inner function. That we may have, let's say, function, we can actually see. Function y is defined as a f of u, but u is g function, g of x, but x is h of t. Right, that we can see. H of t, g of h of t, f of the entire function. This is actually showing you this rule. That we have to differ in order to get the derivative. You will find derivative of f, derivative of g, derivative of h. But f, the first one, depends on everything. You will copy the same formula here. G depends on h, that means we have to copy h, and h depends on t, we will put t, which actually this is nice notation above. Let's see. Differentiate a function square root of secant of x cubed. As you can probably see, square root, secant, and x cubed. Okay, that means derivative of square root, it's 1 over 2 squared. Oh, we can hear something. Who didn't mute the microphone? I can still hear. No, okay, everybody mute the microphone now. Okay, okay. Again, derivative of the square root is 1 over 2 square roots, but we have to copy the same function inside. Oh, am I? Okay, that means derivative of the square root is 1 over 2 square roots, and you notice I copy secant x cubed. And follow the chain rule, derivative of the inner expression. Derivative of secant of x cubed. And now, let's see, copy this because that was here. What will be the derivative of secant of x cubed? Because we see the most inner function is x cubed. That's mean derivative of secant, we had this before, even the chat box is showing me the answer. Derivative of secant is secant tangent of the same input, the same angle. Can you see I didn't change anything? Please do not put x here. Copy the same function, x cubed in this case. And times derivative of x cubed, which of course is gonna be 3x squared. And as we can see, we do have a chain twice. We did apply 2 times because we have 2 inner functions. We have secant and x cubed. Okay, I did put everything on the top, but that's fine. Okay, oh, let's see this. Differentiate sine of cosine of tangent of x. And that's we have to differentiate sine, we have to differentiate cosine, and we have to differentiate tangent. Okay? Because we have 3 functions. Also, please note, we do not have a product here. We're not multiplying anything. It's just sine function, and that's the angle, cosine of tangent of x. Angle of cosine is tangent. Angle of tangent is x. Okay. Oh, I can. That means derivative of sine is cosine, and we will copy the same angle. Okay, times derivative of cosine, because that's it's negative sine, and I will copy the same angle. And the last one, derivative of tangent, is secant square, and we will copy the angle x, of course. Right? That we can see. Sine function is defined in terms of the red expression. That means derivative of sine is cosine, and I copy the same angle. Derivative of cosine, negative sine, and copy the same angle. Derivative of tangent, secant square, and copy her angle. Its angle, not her. X. Right. And we can just leave it. Did I simplify? I did simplify a little bit. I can indicate now that we do have a product. That means I put secant square times, and this is times. We don't have to. I just put, we can even leave it like that because it's nothing to simplify more. Every function has different angle and we can't do anything. Okay, but we can see 3 times. Okay. Differentiate x times, now I see product, sine of square root of x. That means I will apply a product rule, but my second function is compound function. Chain rule will be applied too. Okay, that's mean product rule. Derivative of x is 1. Copy the second function, sine square root of x, plus x, and now derivative of sine of the square root of x. Derivative of sine is cosine of the same angle, okay, times derivative of square root of x, which is 1 over 2 root x. We know that. Okay, and I just put everything on the top of the fraction, and that's it. That means just the point is to apply the product rule, of course, and the chain rule in the middle. I kind of simplify. Okay, I will leave this function for you. I will leave this one for you. Okay, you can pause the video and you can check what I did. And we can try to do this one. find f prime at pi if f of x is defined 5 times sine of x. That means, first of all, let's find the derivative. Derivative of 5 sine of x. That means 5 is constant, we copy constant. Derivative of sine is cosine of the same angle times derivative of that angle, which derivative of sine is cosine of x. Really nice. And we can see we did create a product. We didn't have a product at all in the original function. Okay, let's substitute pi. And who can tell me the values? Because we need a unit circle. Sine of pi. Do you know sine of pi? 0. And cosine at pi? Cosine at pi? -1. -1. Yes, that means this is 0, thank you. And this is -1. And now one more value, cosine at 0. Because you see that 0 was an inner value. Outer value will be cosine at 0. What is cosine at 0? Now it's 1. Thank you, Matthew. Okay, that means this is 1 times -1 times 5, -5. Okay, really nice. Of course, we have to know the unit circle. I just got some nice suggestion from one of the students that what you can do, if you have your screensaver on your laptop or maybe the wall on your phone, put the unit circle, at least for this summer, because you will see every time, and then you will see, and because you can get like a screensaver or the wall, the picture on your front, like the front picture on your phone, and you looking constantly at your phone, right? That's mean put the unit circle for now, and then you will see how confident you will become with your values. Okay, let's see what else I have. Okay, let's try this one. Find the equation of the tangent line to the curve at the point 0, 0, and the curve is defined sine of x plus sine square of x. Okay, that's we have to differentiate in order to get the derivative and in order to get a slope of the tangent. That means slope of the tangent will be the derivative at the given point 0. That means derivative of the function sine of x is cosine of x. And now, do you really get this? Did solve, this was my second or the third example, because this is sine of x squared. That means I have quantity squared. Derivative of u squared is 2u times u prime. 2 sine of x times derivative of sine of x cosine of x. Okay, and then substitute 0, get the values. That means slope is 1. And using the point slope form, I've got an equation, y is equal to x. A really nice curve. And a nice tangent line. Okay, I will skip this one. You can pause the video, okay, and you can go through. It's relatively easy. We'll just do few slopes. Oh, let's do this one as a last question for this section, and I will do implicit differentiation for you today. Okay, find the slope of the tangent line to the curve at the given point 1, 1, and the curve is tangent of pi x squared over 4. Okay, that's really lucky because we only have to find the slope. Slope is the derivative at 1. That's what we have. We do have function tangent of that guy. That means derivative of tangent is secant square of the same quantity, and now times derivative of this quantity. That means what's the derivative of pi x squared over 4? You probably see the answer, but I would like you also to get the answer, to know where I got this. That means pi x squared over 4, derivative will be like that. I can copy pi over 4 because that's constant, and I can only differentiate x squared. Okay, copy pi over 4. What's the derivative of x squared? Can you type something for me? 2x, thank you, I'm just testing. 2 and 4 can cancel out, and that's the answer, pi x over 2. Okay? But please remember, when you see a fraction with a constant in the denominator, never apply the quotient rule. This is constant, that's we can pull out pi over 4 and differentiate the function on the top. Okay, let's substitute 1. Okay, and secant at pi over 4 is square root of 2. Square root of 2 squared is 2. 2 over 2 is gone, pi. That means the slope, pi. Okay. But of course, my point was a chain rule in this case. Okay, I think I have few more, but I can leave it this one for you. Okay, this is equation. Also, please make sure that you know how to differentiate and how you solve the equation. Okay, you can pause the video and you can digest. And I have another one. I have too many problems, but I did type the solution for you to have a learning tool. Okay, of course, always when I ask for the horizontal tangent, please remember, derivative is 0, and we have to just solve this equation. Oh, I have something like that. Okay, let's maybe solve this one, because this one we didn't, I mean, just the type of the question, just in order if you will see again. That's what we have. We have a function f defined as a f compound with g. Okay, and we have lots of values. F of -2 is 8, f prime at -2 is 4, f prime at 5 is 3, g at 5 is -2, g prime at 5 is 6. But we may use all of them, we may use some of them, but we have to find derivative of this function at 5. Okay? That means derivative of the compound function f compound with g is defined as a f prime times g prime. That's just the formula, just the slide that we start with. F prime times g prime. But we remember f prime depends on g of x, g depends on x. And now let's substitute 5. 5, 5, 5. And let's put the values. Yeah, that we can see theoretically is just this. If you know the formula, you shouldn't, we can't really make the mistake. Okay, g at 5, who can tell me the value g at 5? Because I have to be really careful now. Now it's just like a puzzle. It's -2, okay, -2, that means I do have -2. And please check if this value I copy correct. What is g prime at 5? It is 6, okay, thank you. And now what we can see, we have another function, because -2 was not really a value on its own, was the inner quantity. Now can you tell me the final answer? Maybe we can do this way. The final answer is 24. Let's check. Oh, -36. Hang on, what we looking for? Okay. Oh, how did you, positive. Hang on, what we getting? -36, 24, 24. Okay, I believe we have to find this value, and this value is 4. 4 times 6, 24. That means I don't know, Demetrius, how did you get -36? Yeah, 24, okay. Would be nice to see your solutions, but it's okay. Hopefully you figure out your mistake. That's also important. Okay, as we can see, this is nice, also nice question to test a chain rule. Okay, let's quickly start the implicit differentiation, okay? Because that's another techniques to integrate, to differentiate something like complex. Okay, let's see. I will skip this one. It's also a really nice question, but you can try to get the answer before looking at the solution. I mean, you see the solution, but you can cover later. And this one is also really nice. All of the questions came from your suggested homework assignments. Okay, that means I have one more section for today. And for the other section, 2.7 and 2.8, please watch the link. I will provide the video for you, probably this evening. Okay, implicit differentiation. That means that's another form of differentiation. That's what we know. Actually, normally in the classroom, I always ask my students, like, what implicit means. Do you know what the implicit, what's the descriptive word implicit means? Maybe you can type in the chat box. Like, not really mathematically, just as a English, like a language, like what this means, what English dictionary will give us, what definition we will be getting. Implicit. Can you write any synonyms to implicit? Oh, no synonym. You probably know English better than your instructor. No? Oh, come on, you just don't want to share. Okay, let's see this one. What's the difference between implicit and explicit? No, you don't want to write. You're shy. Like in the classroom, I will ask and nobody will raise the hand. I understand. Okay, that means let's see. If you don't want to share with me your English skills, it's fine. Okay, that's what we have. So far, normally, we were like differentiating how can I say, direct formulas, which actually, yeah, explicit means direct, right? That means I can ask you to differentiate y equals to x times sine of x. Everybody can give me the derivative. I can ask you to differentiate this. Of course, the chain rule will be involved, or just any function y in terms of x. Okay, but we can see what's happened. We do have y on this side, only y, and the entire formula is on the other side. That means it's easy to take care of this. We may have the formulas that are defined a little bit different, and we will call like indirect formulas, implicit, in the implicit way. Okay, like for example, this one, x squared plus y squared is equal to 25, or I have first one, and the x cubed plus y cubed is equal to 6xy. That we can see, like, especially the second formula, like x, y are spread out over the left and the right hand side of the equation. And this one is also like, it's not really an equation in y in terms of x. Okay, that means we do have a special method to take care of this. Okay, and we will call implicit differentiation. But what I will do first, looking at my first equation, x squared plus y squared is 25, I think I can still manage to solve this equation for y and use my old methods. Yeah, because it's not bad. I don't think I can do it, this method, with the second equation. That's what I will do. I will quickly apply our old method, which means I will take this equation, okay, and I will solve for x. I'm sorry, for y. One more thing. Do you know what this equation represents? What is the shape? X squared plus y squared is 25. It's a circle. Thank you, good. It's a circle with the center 0, 0, and a radius 5. Okay, that means this is 5, negative 5, negative 5. That we can definitely see, if I will draw a vertical line test, it's not a function. That's probably that we have a little bit of problem. Okay, but what I can do, I can solve for y. Let's subtract x squared, and let's take the square root, and remembering we have positive and negative. That means probably the positive represents the upper semicircle, and the negative the lower, because it's negative. And now, using a chain rule, I can differentiate. Okay, that's my pictures. Derivative of the square root is 1 over 2 square roots, the same square roots, I have to copy this quantity, times negative 2x, because negative 2x is my u prime that we just learned, is derivative of the inner function. And the same on this side. 1 over 2 square root of x times derivative of the inner function. Negative 2x times negative is positive. Okay, that means I differentiate this and I differentiate this. They look almost the same, right? This one is negative, this one is positive, but the 2 is gone. Okay, that means I can do it. Okay, but of course, that's not a point. But let's see. That's mean now, for this equation, if I would like to do the same, I really have to solve this equation. Oh, let me show you actually the curve. Okay, I have to solve this equation for y. Okay, if I would like to do the same what I did with the circle. But we can see this is nice loop. Yes, we call like volume Descartes, but we don't have to really remember the name. It's just a nice loop. And in order to, and I see actually y cubed, that means I'm really assuming if I would like to divide, this curve for the parts that will give me a function, that means, I don't know, maybe I have to take that part, maybe, yeah, depends on the equation. I will probably have 3 different parts. Okay, and I have to solve this, isolate y on one side. But we can see it's not easy. Okay, and what I can do, I can show you that we will definitely not even try this. Right? We will apply the new method, implicit differentiation, which I will introduce in a minute. But I would like to show you these 3 equations. Of course, I did ask a computer to do this for me. And now, please do not be scared. Let's look at this. 1, 2, 3. I mean, this one is 2 and 3. Okay? That means, believe it or not, if we will solve this equation for y, we will get this, and then we will get this. Addition and subtraction is 2 equations. That we can see the first one represents, oh yes, that's what I thought, the part. This is part of the loop, this is the addition, and this is the subtraction. Okay? That's we can see. This is the proof that we will not really do this way. No, 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 no. Who wants to differentiate this? No one. No, we don't really like it. Okay. That's when we're not really doing this. I can even cross that. It's nice to see this, but no, that's not the way. Okay, let's see the way then. That's what we will have. We will use, as I said, the method that we will call implicit differentiation. Implicit, what I was like thinking, like this means that if something is hidden, it's not directly defined, okay? Which you see, like we don't have exactly the function y in terms of x. That means we will take, okay? We will take the equation like it is. We will not change at all, like the equation of the circle or equation of that loop. We will take like it is and we will differentiate. But what we will do, we still have to remember that even if I can't really get the equation for y, I still have the formula for y. That means function y, it's still a function which depends on x. Okay, that means now the chain rule will play a role. That's what I will do. I will differentiate everything. And you will probably have a part x cubed. What's the derivative of x cubed? Can you tell me the derivative of x cubed? You can probably type really fast. Yes, it's 3x squared. Okay, no problem. Now, we will, since we're not changing anything, we will also differentiate expression y cubed. Okay, and derivative of y cubed, maybe you can tell me. Do you think what will be the derivative of y cubed? Okay, something is missing. That's been definitely 3y squared, but we still have to remember that y is my inner function. Behind the y, we do have formula, which of course we don't really know the formula, but we have to respect it mathematically. That's mean correct, y, I mean 3y squared, but also multiply by derivative of y. Multiply by y prime. This is y prime. And this is my chain. Okay, that means, do I have, no, let me ask you, 2x cubed. What's the derivative of 2x cubed? Who can tell me this? Oh, 2x cubed? 6x squared, yes, thank you, Jillian. Okay, and now let's say 2y cubed. Derivative of 2y cubed, okay, it's the same thing, 6y squared, but times y prime. Okay, let's say sine of x. Derivative of sine of x, of course, is cosine of x, but what will be derivative of sine of y? Cosine of y times y prime. That means you can see on this slide, wherever the y is involved, we have to follow the chain rule. We have to multiply by y prime. Because if I will know the formula of y, I will put it there. But of course, I don't want to even know sometimes the y formula. But I'm looking for y prime because that's my point, and I will solve the equation for y prime. Okay, let's see. Let's actually take this circle and use the new method. That's what we will do. We will take the equation like it is, x squared plus y squared is equal to 25, and we will differentiate the left and the right hand side at the same moment. No rewriting, no simplifying. Okay, that means derivative of x squared. Okay, who can tell me derivative of x squared? One more time. 2x, thank you. That means I will write 2x. Who can tell me derivative of y squared? Y squared. Yes, exactly. 2y y prime or 2y dy dx. Different notations, perfect. I'm using dy dx, but I like to use y prime. Yeah, this is y prime. Yes, that means we can see that's the difference. Always, wherever is y, we have to multiply by y prime. And of course, derivative of 25 is 0. And now, since I'm looking for y prime, dy dx, I can solve this equation for dy dx. Subtracting 2x, dividing by 2y, this is my derivative. Okay? As we can see, that's the point. The only thing is, you probably notice, my final answer is in terms of x and y additionally. Okay? Because of course, I don't have the formula for y. If I will have the formula for y, I can plug in here and I will have my normal derivative. But this is perfectly fine. I can have my derivative in terms of x and y. If you see this derivative, probably you will think, okay, the implicit differentiation, like where we use the implicit differentiation. Now let's do one more exercise. Let's compare, because I did this part, I did the other parts, the negative, and I also took the general, I used the implicit differentiation. That's mean I've got this derivative for the implicit differentiation. We got this one for the upper semicircle and for the lower semicircle. And my question is now, are these formulas, both of them, the same like this one? Do you think they are the same? What do you think? Do they look similar? Yes, we have x on the top, x. I mean, we do negative, but we can play with the negatives. And instead of y, yes, you can see we do have square root, and that's actually was y. That's the reason that, yes, both of them if I will substitute instead of y, I will get the same formula. That's mean using the implicit differentiation and having the answer in terms of x and y, we call that this is the most general, like the most general derivative, because that's the general. We don't know the y, and we can still keep that answer. Okay, that's mean this is nice proof that implicit differentiation works. Okay, and what we will do, I have these 3 parts, but let's just do A and B, and we can finish the session. Okay, that's me. First of all, is the same curve, the same loop, x cubed plus y cubed equals to 6xy, and we have to find the derivative, and then we will try to find an equation of the tangent at the point 3, 3. If we have derivative and point, so easy. Okay, that's mean using the implicit differentiation, I will differentiate the left and the right hand side at the same time. Okay. Do I have, okay, I do have my second line. I should like divide it by, okay, that's me. I will ask you, what's the derivative of x cubed? Because I want you to tell me, which it's excellent learning process. X cubed, I think we did this today. That's mean you shouldn't have a problem. Even if you're watching later, you may also try to answer. Okay, what's the derivative of x cubed? I promise, 5 more minutes. 2x squared, thank you, good. Now, what's the derivative of y cubed? That's the tricky part. Y cubed, oh yes, 3y squared and times y prime, or dy dx, it's nice notation. Okay, that's when we have the left-hand side. Now, on the right-hand side, I don't want to ask you because maybe we will get the wrong answer, but please note, we do have a product. That's we definitely have to apply a product rule. One more thing, can you tell me what's the derivative of y? Because this we will have to differentiate just y. Like what's the derivative of x? Okay, let's answer this. What derivative? Yes, thank you, Matthew. Derivative of y will be simply y prime or dy dx. Perfect. That means that's what we have to remember. I can keep this on the slide. We don't have to have derivative of x because it's 1. That means please remember, if you have to differentiate y, you just can't say 1, y prime or dy dx. Okay, that's me. Let's see. You told me this, 3x squared, 3y squared dy dx, and now a product rule. Derivative of 6x is 6 times y plus 6x derivative of y dy dx. Okay, and now I have to solve my equation for dy dx or y prime, that's the same thing, because we're looking for dy dx. Let's isolate them on one side, factor out, divide, and simplify. That means this is the formula. You can probably do this. This was the most important line. Okay, this was the implicit differentiation. I moved the terms with the dy dx on the left-hand side. The other terms I moved on the right-hand side. Factor out dy dx and divide by the coefficient. I mean by this expression. Okay, that's me. Of course, we did expect the answer in terms of x and y, and that's the derivative. And if I will have the formula for y, I can substitute, but you saw the formulas, the whole page. Okay, let's take the derivative, point, and let's substitute 3, because this will be my slope of the tangent. And that means this is, I did substitute instead of y and x, 3, -1. And the point slope form will give me the line -x plus 6. And that's the curve, and that's the tangent line, okay, at the point 3, 3. -x looks good, negative slope. Okay? But the most important is the implicit differentiation. That means I will finish the session. I still have a few examples which you will definitely see on the slides. the solution is typed. That means make sure that you always remember that if y is involved, derivative of y is dy dx or y prime. Okay? That's the only thing for the implicit differentiation. Okay, thank you very much for today. And stay tuned, watch Canvas for more videos. Okay, thank you.